Okay, let's get started. We're moving along with proximate analysis. We covered moisture. We're moving on to the next one, which is ash analysis today. So what's the definition of ash? Very simple though. In simple terms. Let's see. Anybody wants to give any definition for ash? Or yes, Don? Yes, inorganic matter. So anything that is left off after you burn off your organic. That's simple it is. In cartoonish form, you have high temperature, high heat. At high heat, your organic matter gets burned off, oxidized, incinerated, whatever term you want to use. And what's left off is your inorganic matter. And usually, if you're lucky, you get really nice white ash left off. The color of the ash really dependent on the original substance that you have, but in theory, all of black matter, if you look at your ash and it's really, really dark in color, you might think that it's incomplete ashing due to, either the furnace temperature was low or the time was not enough or it's really tough matrix to kind of burn off. But sometimes even if you do everything you can, you don't end up with a really nice white color. But in theory, you go ash. When you look at your ash, if it's white color, whitish color, you would go, okay, I got rid of most of my organic or all of my organic matter. Oops, I'm going backwards. So what's the importance of ash analysis? Why does it matter? Why do we need to analyze ash? Mineral analysis. Yes, that's very much true. Mineral analysis is important. So sometimes we have to determine our mineral content, and in order to determine our mineral content, we have to ash our sample first. Good. Whether it's dry ashing or wet ashing. Yes, to find the percentage of total carbohydrate for labeling purposes. Yes, exactly. So here it is. For labeling purposes, as part of our proximate analysis for nutrition labeling, it doesn't go, ash content doesn't go on the label, but we need it. We need ash content, we need moisture content so that we can get total carbohydrate by difference. And you guys said it already, sometimes we want to do mineral analysis for the labeling. We need iron and calcium, as well as sodium and potassium. They go on the label. So we didn't need to ash our samples in order to determine these mineral elements. Sometimes we do not need to ash our sample for salt, for example. We'll talk about that in mineral analysis chapter. But in most cases, you need to ash your sample to determine your mineral content. You know the cartoon Popeye? Popeye the sailor man? He eats the spinach and he becomes very strong because of the high iron in spinach. Okay, sample preparation. Depending on your food sample, it's sometimes recommended to dry your sample. If your sample is really high in moisture, it's going to cause splattering. So it's kind of like if it's a plant material, really high in moisture content, it's better to dry it first. And after you dry it, you homogenize it by grinding. Same with meat. Meat is also high in water content as well. So it would be good to get to dry these samples prior to determining ash. So you can dry them actually, dry these samples using official methods of analysis for drying. And like we learned in lectures previously, and some of you already done the lab. And then you can determine ash, you can determine protein, you can determine fat on dry bases, and then you can convert to actual bases or wet bases before drying if we know how much moisture we want. Some products foam. sugar products foam. And some products smoke and burn, like cheese, because they're high in fat. So, in order to prevent the foaming, because if you put your sample in the muffle furnace where we put them to ash, and at very high temperature, they start foaming and the foam spills out off of your crucible. And then what happens is you lost sample, you kind of have an erroneous result because you lost the sample. So you might get underestimation of ash content. Same with cheese. If they smoke and burn, then also you might end up losing sample and underestimating. So it's best to heat up these samples prior to putting them in the muffle furnace. Sometimes we put them on a hot plate and then you let the cheese, that's what you're going to do. Some of your groups in the lab that have cheese, we put them on a hot plate, allow them to burn and smoke, and when they're done burning and smoking, we can put them in the muffle furnace. So when we, let's say you dried the sample, you need to mill it, or even if you have cheese, you want to grate your cheese. So the idea is to increase the surface area and enhance sampling procedure so that your sample is homogeneous, you have mixed it well. But sometimes grinding can be a factor of contamination. If you're grinding in a metallic form grinder, coffee grinder or whatever grinder you're using, and it's made of metal, the compartment, that might cause some metal contamination and overestimation of your ash content. So something to be aware of. Sometimes if we have high fat samples, often, well, if you're able and you have the capability to do that, you extract the fat, measure the fat content, and determine the ash on a defatted sample. That also can happen for, let's say, meat. You dry the meat, you defat the meat, and what's left, the residue, you determine the ash content in that residue. And then you back calculate. If you want to determine how much ash you had in your original sample, you need to know how much moisture there was, how much fat you took out, so that you can account for that in your calculation. We'll have some example calculations later on. Okay. So ashing methods. We have dry ashing, wet ashing, and microwave ashing. Microwave ashing can be dry and wet as well, and we'll talk about that later. With dry ashing, that means you just weigh your sample, put it in a crucible, put that crucible in the muffle furnace, dry ashing. Sometimes you mix dry ashing with wet ashing. What does that mean? Sometimes you have a sample that is hard to kind of oxidize and burn off your organic matter. We put it in the muffle furnace, we take it out, we put some nitric acid to help with oxidizing the organic matter, heat it on a hot plate a little bit, and then ash that again, put it in the muffle furnace. Wet ashing is completely wet ashing. You do not use the muffle furnace. You digest with strong acids, and we'll talk about that. The difference between dry ashing and wet ashing is essential in a sense if you want to get ash content. So you want to get ash percentage, you really have to do dry ashing. So you can get a weight measurement of your ash or your inorganic matter. In wet ashing, you don't get a weight of ash per se because you're solubilizing the ash in the acid. So you put acid in your sample, all of your organic matter is going to oxidize and burn off. What's left is your minerals or inorganic substances in the acid. So you don't necessarily get a percent ash if you need a percent ash. So if you want percent ash for approximate analysis and for labeling purposes, you really want to get an actual ash content using dry ash. So muffle furnace is the oven that you use to burn off your organic matter. So it comes in different sizes, and usually you can heat up really high temperature. You can reach up to 900 degrees Celsius temperature if you want. But oftentimes, all of the official methods of analysis for different food products, they range from 450 to 550, around that range. So you put your samples in. Usually you want to put your samples in when it is cold before you heat it, because it gets extremely hot. Don't want to put your hand in there when it's hot. So usually you put your samples in, you close, and you turn it on, and it gradually gets up to temperature. Same when you want to remove your samples, you want to make sure you turn it off, let it cool, and then take your samples. Same with everything, you get to select different containers to do the ashing. The common one that you see usually in labs is that porcelain one. Let me see if I can, this one. This is what you usually use, and that's what we've used in the lab for you guys. It's durable. Um, one of its disadvantages, if you change temperature very quickly, it might crack. So it can crack potentially. But it's the most common um, crucible we use is the porcelain. And it's very hard to label, so we need to get a special pen. I think uh, felt tip pen, where we label it in the bottom, usually at the bottom. Or if you use a pencil, you can also label with a pencil. So that's the one we use usually. There are many other options like quartz, for example. It's very expensive, but it also maintains or doesn't crack, so it sustains high temperatures and also changes in temperature. It is resistant to acidic foods, so it's a good crucible. Steel is another common one that is used that is durable to different pH samples, but however, there's potential contamination because steel might have cadmium or nickel, so it would cause contamination. Um, the quartz fiber, this is the quartz fiber. It's not reusable, disposable, I meant to say. It is durable, have similar characteristic to the quartz, but the additional benefit it's porous. So the temperature transfer is faster, so you get ashing faster using these kind of crucibles. The best one is the platinum. It's durable at high temperatures, durable to changes in temperature, to acidic, alkaline pH. Um, it's basically very good crucible, the best one, but very expensive. So you won't see it in labs where you have to do routine ashing, where you have to use a lot of samples, and so you won't usually see it in labs. Okay. So like everything, dry ashing has advantages and disadvantages. If you are careful when you put your samples in, it's not hot, and when you take them out, it's not hot. So relatively safe. You just make sure that your furnace in the lab is situated with the hood so that all the fumes that can come out is sucked up in the hood. And it doesn't need much attention. Put your sample, you go, you come back the next day and get the samples out. You don't need any reagents, well, unless you are doing the mix between dry and wet ashing. Um, so no reagents or blanks if you're just doing pure dry ashing. Many samples can be analyzed at once depending on the size of your furnace. We have multi-furnace are small cubicle ones. You can potentially put 6 samples in. And we have the bigger ones where you can put up to 12 samples or more depending on the size of the crucibles. Disadvantages, it's lengthy. Usually you need 8 to 12 hours to kind of get all of your organic matter burned off. Initially, it's expensive, but once you have it, it's a workhorse. It just stays for a long time or stay functional for a long time. Another disadvantage, we might get volatilization of some elements because some elements volatilize at lower temperatures than others, such as iron, zinc, copper. So you get volatilization, so you get underestimation of ash content and potentially underestimation of individual minerals if we're doing mineral analysis. So sources of error, from everything we talked about, what do you think sources of error in dry ashing could be? We talked about a few already. Yes, Don? Contamination from steel if we're using steel crucible, contamination from grinding if we're using metal compartment or grinder where your sample is put in metal compartment. Yes, contamination. Let's see. Yeah, well, residue in crucibles. Usually you kind of work with crucible that's been pre-ashed or acid washed as well. So you acid wash your crucible, you pre-ash them so there's nothing in there. Foaming over in the oven, yes, that's why we want to make sure sample handling, depending on the sample we have, we pre-dry it, defat it, or put it on a hot plate to get rid of the at lower temperature than would be in the muffle furnace to get rid of the foaming and to gently get rid of the foaming and also the burning and the smoke. Okay, let's see what else I have. So this is common, sample not representative. You have to think every time we say what are the common sources of error in anything. Really, sample preparation and selection of sample from the population, whatever is your population, the population, a bag of sample or cans of product, whatever is your product, sampling is very important. Taking a representative sample, that's your chapter 5. That's a very important chapter. We have a makeup lecture on it. So if your sample is not homogeneous, your sampling will not be representative of the entire sample. So it's very important that we have a homogeneous sample and we get a sample that is representative of the population. Contamination we talked about, loss of sample, during drying, if we're not careful, if we got splattering, if we lose sample due to foaming, if the heating that we're doing is also aggressive. So we really have to be very careful handling the sample after weighing it in the crucible. Talked about volatilization, incomplete combustion. I think we talked about it earlier. When your ash is dark in color, most of the time, that means you still have organic substances there that has not been ashed properly. That causes an overestimation of your ash. So you're potentially assuming that you have more ash than there is if the sample was not completely combusted. Let's do some calculations together because you're going to be doing a lot of these calculations on wet bases, on dry bases. So let's take out a piece of paper and then Laura's going to create a +2 extra credit on Canvas where you would take a picture and upload it. So let's calculate ash content on dry bases. So take out a piece of paper and let's do that calculation together now. Give you a couple of minutes, and when you have an answer, share it. 2.5%. So let's see, we've got an answer. Let's try to solve this together. So what's the given? The given is I have 1.14% ash. And then I have 47% moisture. I want to determine percent ash on a dry basis. So I want to know how much X is in 100 grams of solids. So I'm looking for X in 100 grams of solid, XF in grams in 100 grams of solid. So percentage on solid basis. What do I have given? I have 1.14 grams in how many grams of total solids? If I have 47% moisture, what are my total solids in grams? Out of 100 grams, how much do I have total solids? I have 47 grams per 100 grams moisture. What would be my total solids? 53 grams. So I have, out of my 53 grams in 100 grams total sample, I have 1.14 grams of ash. So what would be my percent ash in 100 grams solids? So basically solving for X. So 100 grams times 1.14 grams over 53 grams. I'll get my grams per 100 grams, which is 2.15 grams per 100 grams. That means percent. So that's the quick answer right there. But here is the explanation: is I'm looking for X grams in 100 grams solids, and I have 1.14 grams and 53 grams solids because I subtract 47 from 100. I know how much I have total solids. Then I calculate, solve for X, calculate for ash on dry basis. Okay, when you want to know if you put the numbers correctly, and if your ash content or any content on dry basis is higher than your wet basis, then you kind of did the math, you put the numbers correctly. If your content on dry basis is lower than the content on wet basis, you kind of did something opposite. So always your dry basis percentage is higher than the wet basis percentage. Okay, so this is kind of a check for you to know what you're doing. All right, so what is the ash on fat-free basis? So here we have a meat sample. So sometimes you dry and you defat so that you take care of splattering, smoking, anything. You have a fat-free, moisture-free sample, and now you have to calculate your ash content on fat-free sample or fat-free basis. Okay, how do I do that? Give it a thought. You have the percentage of fat on dry basis. You have it as 56.6%. So now you have the fat on dry basis. You want to calculate it on wet basis. So that is your hint here, is calculating the fat on wet basis. That means on as is, before you remove the moisture. Okay, so you want to calculate fat on wet basis, that's first. And once you calculate fat on wet basis, then you can calculate ash on fat-free basis. All right, let's give it a go. So what's the fat content on what basis? Did anybody get that? Fat content on what basis? Yes, 30%. Yes. So how did we do that? The same way, the same manner of thinking. We have 56.6 grams of fat in 100 grams of solids. This is fat, solids. That's what the given is. 56.6 grams per 100 grams of solid. I'm looking for what basis when I had 53 grams of solids. Okay, so basically solve for the x equals 30 grams per 100 grams, then it is 30%. So now I have my fat on what basis to 30%. So if I have ash 1.14 on what basis, what would it be on fat-free basis? Do we have any? Okay, so we have answers, 1.63, yes. So basically, what you do in this case, you already have the fat content is 30% on what basis? So 30% fat on what basis? So I have 1.14 grams of ash let's see here. And how much? I have it in 70 grams of the remaining. How much would it be in 100 grams? Okay, so 70 is everything minus the fat content. So 1.14 grams over 70 equals x over the 100. 100 grams of everything except the fat. All right, so this means if you solve for x, it will be 1.63. So the 70 is 100 minus 30, which is the amount of fat you have on as-is basis or wet base. Okay. Good. What is today? Monday? Wednesday by 5 p.m. Okay. All right, so wet ashing. So wet ashing here is, again, like I said earlier, here we're using strong acids, highly strong acids that can oxidize organic matter or burn off organic matter. So they usually use a combination to make sure that all of your organic matter can get oxidized. So a common combination is nitric acid and perchloric acid. However, perchloric acid is it's a dangerous acid, it's explosive. So in order to be able to use perchloric acid, first you need to have a specific hood, perchloric acid hood, and also you have to have specific training to be able to use this perchloric acid. Safety training for the use of this acid. Often we do not have perchloric acid hood, so you use instead a combination of sulfuric acid and nitric acid. So what happens is when you put your sample in, you want to heat also as well, put them on a hot plate. So what you see here is kind of a heating block that we use. See, let me take the chat box a little bit over to here. So you have a kind of a heating block with these tubes that you would put your sample in, you add your certain amount of acids, and then you heat to about 200 degrees Celsius. You also need to have them all in a hood where once the sample are burning, you're going to see very dark black color and fumes. So you see fumes coming off and your sample slowly go from dark black burnt color to brown to light yellow, straw yellow, you call it, solution. So clear, light, straw yellow color. So that means your minerals now are soluble in the acid and all of your organic matter is burned off. In this kind of ashing, you always need a blank. Because if you are determining mineral content, which that will be the purpose of wet ashing, you need to make sure you have a reagent blank because you want to correct for any contamination like you did when you solubilized your ash for the AA lab. So you would also need the reagent blank. So basically you do the exact same thing, you tube with the acids, but no sample, and it runs through the whole procedure. Okay, so advantages and disadvantages. So advantages mainly if you're after element analysis or mineral analysis, your minerals remain in solution. Basically, you don't have a volatilization because the temperature is much lower than in a furnace. So no volatilization in this case, and you have shorter oxidation time. So a couple of hours basically. Disadvantages, you need constant operator attention. So you cannot just put your sample and come the next day. You should be around in the lab, monitoring your sample. You are using corrosive reagents, and you can handle a certain set number of samples at a time. Usually 4 to 6, maybe, depending on how many digestion blocks you have in your heating block. So microwave ashing, this is not yet an official method of analysis, but there has been studies that did comparative testing between a muffled furnace, let's say, and a dry ashing using microwave. There's comparative results among them. You can do microwave, whether wet ashing or dry ashing. You can do wet ashing as well in a microwave, so it's also shorter time of analysis. Um, you can, in microwave wet ashing specifically, you can operate under pressure. So if you increase the pressure, the boiling point increases of the acid as well. So you can maintain the acid and have more efficient digestion than if you don't have pressure. The boiling point will be lower. At atmospheric pressure, some of the acid might evaporate and you won't have that much efficiency. Because you can operate under pressure, you can use less corrosive acid, such as nitric versus perchloric, and you can use multiple samples at the same time or process depending on the type of microwave you have. So let's say this microwave, you can have up to 40 samples in the compartment, and you can operate under pressure as well. So it can be very efficient and quick. There are also open vessels that are under atmospheric pressure, but these are used when you want to process large volume samples. So dry ashing, it would be similar to your dry ashing using regular muffle furnace. Here you get results in minutes, potentially 4 to 20 minutes, depending on the sample that you're analyzing. So that's the benefit of that time, but it's not yet an official method, but there are a lot of comparative studies that the book chapter talks about. So let's think about this together here. You are determining the total ash content of a product using the dry ashing method. Your boss asks you to switch to a wet ashing method because they think or they have heard that it takes less time than the dry ashing. Do you agree or disagree with your boss concerning the time issues and why? And the second part of it, not considering the time issue, why might you want to continue using dry ashing? So they're kind of related to each other. And why might you change to wet ashing? So what would make you agree with the boss or disagree with the boss? In what circumstances you would agree and what circumstances you would disagree? Basically, that's what the question is. Disagree needs special hood and training. That's one perspective. Okay, especially if you want to use perchloric acid, yes, okay, it's more involved and you need training and safety. Okay, that's one answer. What else? Yes, if we want total ash content, that is a key point. That would be one of the things that it depends on the objective. Why are you doing ashing? What's the purpose of ashing in your company? Are you ashing to get total content of ash for proximate analysis? Or are you ashing to do mineral analysis? If you're ashing to get total ash content, that ends the discussion right there and then. You can just educate your boss and tell them, the wet ashing won't give me total ash. Okay, that ends the discussion there. If you want to do mineral, yes, exactly, volatiles. So if you want to do certain mineral and you want to be very careful and accurate, and you don't want any losses due to volatilization, then you might say, okay, yes, wet ash. I need to calculate my copper content, my iron, my zinc. I need to be very careful with losses due to volatilization. So again, here the highlight here is what's your purpose. So you want to be sure to ask yourself the question, what's the purpose of this analysis? So that you can choose the right method for it. And what's the time involved, what's available, what kind of training you need. So there's so many factors you need to consider, but first and foremost is what's your objective of that analysis. Okay, so last year I want to show you, which might not be in your slides, I just put it in this morning. It's actually in your chapter, table 16.1. So this gives you a range of where your ash content is. And this is not the complete table. I just put it there just to show you the importance, what I'm trying here to draw your attention to is the range of your ash. So you want to know potentially where the range of the ash content is. It's, you see here, it ranges some in the decimal, something less than zero, less than one to a little bit close to 2%. That's mostly where your food products, food ingredients are. There are some ingredients that might get some flour, for example, or ingredients that might get up to 4% ash, but really that's the range that you normally see in your products. So oftentimes I ask this question in a quiz or an exam, which won't be on the midterm because this part is not included in the midterm, but maybe in the final or the following quiz. I asked you to create your own data. Sometimes I tell you, here's the food product, create your own data and calculate based on moisture, wet bases, or dry bases. So you want to know where an approximation of where ash content could be and where is moisture content and be realistic. So in cheese, for example, carbohydrate, total carbohydrate cannot be 50%. So you want to make sure your values are reasonable. If I ask you for a cheese sample or a flour sample, where your percentages could be a range. I'm not going to be asking for the exact number, but at least a range of it. That's why it's important to show you where ash content is. Okay, so that's it for ash content. I'm quickly going to introduce fat analysis and we will continue with fat analysis on Wednesday. But just a quick introduction. I have 5 minutes, so I will introduce that. What happened? Okay. So now we have done moisture, ash, and next is fat analysis. That doesn't look good, does it? All right. So the following is true. The term lipid can be used for both oil and fat. Oil has higher melting point than fat. Fat has less saturated fatty acid as compared to oil. That's a little bit of, food chemistry, trying to remember your food chemistry a little bit. Because a lot of the analysis we're going to talk about here and later when we do fat characterization chapter require you to know some of these basics. Okay, let's see. We're getting a lot of different answers, but one correct one that I see is A. So A is the only correct one. So lipid is a term that is used interchangeably for oil or fat. Oil is liquid at room temperature, fat is solid at room temperature. So fat has a higher melting point than oil. And fat has less has less polyunsaturated, has more saturated fatty acid. With more saturated fatty acid, you have higher melting point. So oil usually has more mono and polyunsaturated fatty acid than fat does. So the only correct answer is A. Lipid portion of the food can include vitamin A and B, consist of fractions with varying polarities, cannot be completely extracted using ethyl ether. Anybody gonna take, yes, Michelle? Okay, so A and B, so somebody said D or G. Yes, so it is actually G. So Sorry? Yes. It is all of the above. I had to look for a second. Yes, it's all of the above. So vitamin A actually addict, A, D, E, and K, all the vitamins that are fat soluble vitamins will be present in or counted into your lipid fraction. Um, and definitely you have fractions of different polarities. So triglycerides are very hydrophobic, whereas mono and diacylglycerol, phospholipids are more polar and can be soluble in polar solvents. And sometimes in polar organic solvent, more polar organic solvent, methanol, and also some phospholipids can be soluble, monoglycerols can be soluble in water. Also, short chain fatty acids can be relatively soluble in more polar solvents. So the fat or the lipid fraction of your food has varying polarity. And because they have varying polarities, there's not one solvent that would extract all of your lipid components effectively. That's why diethyl ether, yes, is not necessarily the perfect solvent to extract everything. Sometimes we use a combination of solvents, PET ether and diethyl ether in combination. So you'll be doing that in the fat analysis lab where you will be using combination of solvents, try to get extract as much of your lipid fraction as possible. So G is the correct answer. All right, I'll stop here and we will continue on Wednesday. Yes, what's that? Yes,